project in cooperation with our international partners. So I'm going to start this event contextualizing you all about the project that we are presenting today. So please let me share my screen. Second, please. Okay. So COVIBOT, the COVIBOT project was a research project that was formulated last year in the beginning of the pandemic, and is a project that is supported by the Royal Academy of Engineering and the Colombian School of Engineering. As we can see here in this image, this project gathers researchers from all over the world, particularly from United Kingdom, from Brazil, from Argentina, from Chile, and from Colombia. The idea of this, the initial idea of this project was to develop technologies to combat and tackle the effects of the COVID-19 pandemic using technology, artificial intelligence, and different strategies that we have been working previously in other projects, and how we can use them to combat and to manage the COVID-19 pandemic. As we can see here in the right image, the first proposal of our project was composed of 6 elements. We plan to develop firstly a mobile platform for disinfection task. Then we wanted to develop a smart room system that was in charge of scheduling and prioritizing the disinfection tasks in indoor environments. This also was going to be implemented with the mobile disinfection platform. The third module of the project that we planned at the beginning of the project was a biohazards detection module that was in charge of detecting the proper use of face mask in people, and also the detection of hazardous situations, for example, when people are not abiding by the restrictions of social distancing. And also we propose a fifth module about outdoor surveillance using drones. And finally, we wanted to implement all of these technologies in a centralized cloud server. However, with the development and the process of the different activities of the project, we found out in literature and in evidence, in clinical evidence, that these 3 modules that we are now seeing in your screens are the most important ones. So these are the modules that we're going to see today in our seminar. The first one is the disinfection platform that is going to be presented by one of our researchers. Then the smart rooms and autonomous navigation system to optimize those disinfection tasks. And finally, the third phase, we also found in evidence that it is more important to focus in indoor environments than outdoor environments, because the risk of contagion is higher in these situations. So with this information, we are going to start with the event, and we would like to start with introducing our international partners. So please let me introduce our first speaker, Professor Subramanian.
Hello.
Hi, Professor. I'm going to introduce your profile. So just 1 second. So Professor Subramanian Ramamurthy is a personal chair in robot learning and autonomy in the School of Informatics at the University of Edinburgh, where he's also director of the Institute of Perception, Action and Behavior. He's member of the executive committee of the Edinburgh Robotics Center and a Turing Fellow of the Alan Turing Institute. He received his PhD in electronic and computer engineering from University of Texas at Austin in 2007. He has been elected a fellow of the John Academy of Scotland at the Royal Society of Edinburgh, and a visiting professor at Stanford University and the University of Rome La Sapienza. From 2017 to 2020, he held the position of Vice President of Prediction and Planning at 5AI, a UK-based startup developing technology for autonomous vehicles. He continues to be involved with the company as a scientific advisor. His research focused on robot learning and decision-making under uncertainty, with particular emphasis on achieving safe and robust autonomy in human-centric environments. His work has received funding from a variety of sources, including EPSRC, the European Commission, DARPA, the STL, and the Royal Academy of Engineering. He is the PI of the UKRI research node on governance and regulation of trusted autonomous systems. So Professor Subramanian, welcome to our seminar, and thank you again for joining us in this project.
Thank you for the introduction, Sergio, and it's a pleasure to be here. Let me try to share some slides. Do you see my slides?
Yes.
Okay, very good. So in the time that I have been given, I want to kind of set the background for some of the work that we've been doing. So it has been my pleasure to be part of this project. And during the rest of this meeting, we are going to hear from a number of people who've been involved across many different countries in what they've achieved in terms of building systems specifically for pandemic preparedness. I want to take one step back and talk a little bit about what is the state of robotics and autonomous systems, and how is it being used, not just immediately for how we've managed to deal with COVID today, but looking forward a few years into the future as we kind of, every country makes its response and economic recovery, what are the technologies that we would like to bring to bear so that robotics and autonomous systems can play an effective role. So this was a diagram that was prepared early in the pandemic. So this is from a paper by Robin Murphy and collaborators who have a long history of working on, rescue and field robotics. So
sorry, Raman, I don't know if you are showing in full screen because we are seeing the presenter screen.
Okay, let me see how to fix this. Is that better?
Not yet.
Not yet.
No, not yet. I'm trying to figure out in Teams which that option is. So do you all know what the option is for going to just the full screen?
Or maybe start shading and shade again to see if...
Yeah, so let me then stop sharing and start again, and I will do it differently this time. Do you now see my main window?
Great, that was great.
Yeah, okay. Yeah, so where was I? Yeah, so this was a picture that was created early on during the pandemic, and it was intended to show the number of different ways in which robotics can be used. So as you can see, this ranges from care home or kind of assistive operations in the hospital or the laboratory, sometimes in the clinic, all the way to just public uses such as delivery robots and kind of disinfecting public spaces and so on. So there's a wide variety of ways in which robots can be used. And what this picture is also showing us is that there are some things that were already ready to go as soon as people realized that they were needed, such as disinfection is one example. And there are some things that are absolutely necessary going forward, even after the immediate restrictions have been lifted, such as laboratory automation or robotic assistance, or kind of taking care of patients, especially when the healthcare systems are stretched. And so I want to give you a flavor for where do we think we are as roboticists? How close are we? So I want to pick on this theme of remote operation of robots and what technologies are available and how do we think they can be used. So here's the first example I want to show you. This is a system in my lab where you see a person remotely operate the robot. Now, for the purposes of this demo, they're standing next to each other, but you can easily imagine that they are physically separated quite far apart. In particular, the robot can be inside hazardous and kind of difficult areas, and the human can be outside. And what we want to show here is the degree of dexterity with which such remote operation can actually be carried out. So the person is wearing a sensor on their hand, which is picking up EMG signals. And depending on a few different gestures that we've given to them, they can control the multiple degrees of freedom of the robot arm. So not just the hand and the arm, but also the ways in which the wrist has to be manipulated and exactly when something should be picked up and so on. So this is the kind of technology that can be brought into the mix. Another technology that we've been working on quite a bit is to try to find out if the core operations that are sometimes being performed, such as, let's say, a medical examination, can actually be automated in the sense of we look at what a medical expert actually does. In this case, it's a postdoctoral researcher in my lab, Dr. Michael Burke. He's demonstrating to the robot what it means to perform an ultrasound scan. So we have a standard medical grade ultrasound machine, and he's looking at this phantom, which has the equivalent of a tumor in it, and then he's showing how he would go about searching for it. And so from looking at the images that the ultrasound produces and also the pattern of movement that the human expert adopts, the robot has learned what it means to perform a good exam, such that in future it can try to perform that examination autonomously. So here the human has been taken out of the loop and the robot is automatically scanning for itself, trying to look for, where are the abnormalities. Now, you can imagine that this could be placed in an emergency room setting. This can be placed in, a number of different settings where, let's say, if you're under infection control, you don't want to expose everybody in the care system to that infection. You can have some of it be handled by an automated system like this, and only a few people who need to actually get involved. So that's this is the kind of technology that's becoming possible and that we are developing in the lab, and soon we hope these kinds of techniques can actually be deployed. And the final example I want to give you comes from a different project that's called Orca Hub, which pertains to robots operating in difficult remote environments. This particular work was done in the context of inspecting oil rigs and offshore assets. But as you will see, the underpinning technology that's being used there can easily also be adopted in, let's say, a hospital environment or inside a shopping mall kind of environment. Now, this video I'm going to play has audio of its own, so I will be silent while hopefully you hear the audio that's associated with the video clip.
Robots are an invaluable asset in remote environments, as they can keep humans out of danger. Here we have a remote platform where robots are expected to inspect and maintain it autonomously, whilst communicating with remote operators through a human-robot interface. Using semi-supervised learning from demonstration, a robot can learn from a mix of labeled and unlabeled data to navigate and operate in a dynamic environment. Explaining the behavior of the autonomous robot is challenging. Even experts may fail to communicate the decision-making process while controlling complex systems. Robot operators use an array of interfaces to check what the robots are doing and need to understand their reasoning in case they have to intercede. This is made even more complicated by the multiple types of robots with different behaviors. Here we present a system for self-explainable robots that synthesizes natural language reports about what the robot is doing and why. The reports are simple and straightforward, designed to keep the operators informed without overloading them with information. They work as an add-on to semi-supervised learned models that control the robot, and are model and domain agnostic to keep them flexible in dynamic environments. Let's dive deeper into the system. The first part is to learn from a demonstration. The operator remotely performs a demonstration of what the robot should do in the platform. From the demonstrations, the system is able to extract high-level goals and train a neural network that predicts the operator's actions. We use the goals and the neural network to autonomously control the robot and synthesize more complex behavior based on the combination of the goals. The path towards the goal is generated dynamically based on the obstacles that the robot detects in its surroundings. Next, using the model and inferred goals, the system can perform inference analysis. The most important are the sensitivity analysis to detect salient objects, so those that most influence the robot's path predictions, and counterfactual analysis, which allows the system to check for modifications of the scenario that will solve the task. As the high-level goals, object saliency, and behavioral prediction are in the state space, they can be directly represented as marks and figures in the sensor images. To improve transparency, we feed these data into the natural language generation module to produce reports in natural language about what is happening and why. This allows for the display to be much simpler, and thus it can reduce the information overload of the operators of these remote autonomous robots.
So these were some snippets of state-of-the-art technology that we hope gets used more widely. So to conclude, I want to say that the COVID pandemic has incentivized the adoption of robotics and autonomous systems technology. Even just in private life, we see people much more receptive to looking for ways in which technology can help them cope with the difficulties. And all of this technology builds on a substantial research base that has been developed in robot learning, human-robot interaction for many decades now. And it is my hope that, beyond the immediate needs, even as the recovery proceeds for many more years to come, RAS will play a crucial role in helping us navigate that. So with that, I will stop. Thank you very much. I'm happy to have a discussion during the rest of this meeting.
Okay, Professor Subramanian, thank you very much for your presentation. Very interesting, the developments that you are working on in your lab. Just also to clarify to our audience, at the end of the event, we are going to have a proper space for questions and discussion if you have any question for our speakers. Okay, so now I'm going to introduce the presentation of Professor Marcelo. Professor Marcelo was born in Brazil. He received the degree of mechanical engineer with emphasis in mechatronics in 1993 from the University of Sao Paulo, Brazil. Subsequently, he received the Master of Science and Doctor of Science degrees in mechanical engineering in 1997 and 2000 respectively from the State University of Campinas, Brazil. During his Doctor of Science studies, he spent 8 months as a visiting student at the Institute of Robotics of the Swiss Federal Institute of Technology in Zurich. From August 2005 to July 2006, he spent a sabbatical year at the Autonomous Systems Laboratory at the Swiss Federal Institute of Technology in Lausanne. From 2001 to 2008, he was an associate professor at the Pontifical Catholic University of Minas Gerais, Brazil. From 2002 to 2005, he was also co-director of the Mechatronics Engineering Department and the Robotics and Automation Group at the Pontifical Catholic University of Minas Gerais. Since 2008, he has been a professor at the University of Sao Paulo. He has published more than 100 papers in the field of vehicular dynamics, mechanical design, and mobile robotics in several conferences and journals. His research interests are mobile robots for agriculture, inspection robots, vehicular dynamics, design methodologies and tools, mechanical designs applied to robots and mechatronics. So Professor Marcelo, welcome to this event and thank you again for joining us today.
Thank you for the introduction. I will try to share my short presentation. Let's see if it's going to work. Can you see my presentation now?
It's loading.
And now?
Not yet.
Okay. I always have problems with Windows.
Okay,
and
now we're
Apple.
seeing it.
You're seeing it, okay. So, and now?
We're watching Teams.
Just Teams. Gosh. So I'm not sure if it's gonna work. Oh, here. Okay.
Okay, now we're seeing Keynote.
Good, but the presentation or the presenter?
No, we are seeing the presenter view.
Over. Yeah, definitely Microsoft Windows and Apple, they don't like each other. So let's try to do it here. Maybe be easier. Otherwise, we are going to spend too much time. It's good for you?
Okay, it's okay.
Okay, so I'll try to make it short. I'm from University of São Paulo in Brazil. We are not in the capital of the state, in São Paulo City, but we are in São Carlos. And São Carlos is basically a young city where we have not a very big population, but we have lots of students. And since the COVID started, we needed to stop all the universities here to avoid that the students could get contagiated by COVID-19. Okay, so here we have a view of the city. Basically, the actions in our university in São Carlos were in the engineering school and in the physics institute. Okay, and most of the research done trying to help our government to stop COVID-19 was carried out in this institute, Centro de Pesquisa em Óptica e Fotônica, or it means Optics and Photonics Research Institute. And we start to collaborate with them developing some systems, okay? We have a web page here, and we work in this area, innovation. And it was very interesting because some of the solutions that we used were already being researched for, let's say, 7 or 8 years ago. So Professor Vanderlei Bayat, that's the dean of this research institute, he was working on the use of optics and photonics, trying to eliminate bacteria and other microorganisms for a long time, okay? We are part of this robotic center, and those here are my colleagues. We have a very good collaboration with the Federal University of São Carlos. And my group, actually, we don't work with robots for indoor use. We work on field robotics. That's one of the reasons that we didn't start developing robots here that could do disinfection. But on the other hand, the São Paulo State Foundation, Research Foundation, they start to apply money in some small companies that had this idea and trying to make them in a fast way to have a product that could be used in the hospitals. When it comes to COVID-19, you know, the situation in the world now is getting better. We are in the third wave, but in Brazil, our situation is not that good compared to other countries. We are the number 3 in cases, and in this deaths per million of population, I think we're some of the worst ones. Okay, today the situation is getting better, but with this Delta variant, maybe we are going to face another wave. We have at this moment around 600,000 deaths and more than 20 million recovered people. Okay. In this scenario, what we did in partnership with this optics and photonics group, we start to get some financial support from state research agencies and from companies and the Embrapi, that is a federal agency that invest money on small companies, trying to have in a short period of time products that could be used in the hospitals. One example of product is this. It's a very light, and you can use with your hands to eliminate microorganisms. But this was done in 2014, so this product was ready. Companies were already using it, and we found a way to make it more visible for the users. And they start to develop other products too. So we, in the mechatronics group, we helped the optics and photonics group with the electronics and other things that we could collaborate with them. And in this way, in a short period of time, they start to develop other products to decontaminate water, to decontaminate the air in closed environments. This was something very interesting for schools, hospitals, and other places. And back at the time, this was made in the end of last year. Back at that time, they start to use this also in the football or soccer fields, so they could use that. The soccer players could have a free environment to run the games. And here I have a short move for you. It's in Portuguese. Probably you're not going to hear the sound. But this is from the São Paulo state government, showing the use of this photodynamic therapy to avoid these secondary infections that come from COVID-19. And they are using this technology to help the patients. So how this research was carried out in our university here in São Carlos.
And no, we're not hearing the audio.
Sorry, I didn't hear you. Okay, can you hear me?
I was saying that we didn't hear the audio from the video.
Okay, but anyway, you have the link here, so I will send you the material, the PDF, and later you can check it. It's about the use of this photodynamic therapy, trying to avoid the secondary infections that the COVID-19 patients have after getting COVID-19. So they can use all these machines inside the hospitals and also in clinics to try to avoid these infections. Okay, and I'm almost concluding here. When it comes to USP, we have many university hospitals around the state, and today some research groups are also trying to get other medical or drugs that can help the treatment of COVID-19. And the São Paulo Research Agency is also, they invest money around 20 million reais. It's not that much, but for Brazilian standards, was a good money. And they supported more than 20 projects in São Paulo State projects relate to the medicine schools, to development of new drugs, and also new machines that could help the patients. Basically, this is what we did in our group. We helped the CEPOF, this optics and photonics group, and the university as a whole also tried to help in this situation. Thank you.
Okay, Professor Marcelo, thank you very much for your presentation. It was amazing. So now I'm going to introduce the talk of Professor Ricardo Carelli from Argentina. So just let me introduce his profile first. Dr. Ricardo Carelli was born in San Juan, Argentina. He received his PhD in electrical engineering from the National Autonomous University of Mexico in 1989. He's a professor at the National University of San Juan, and he has reached the highest category of senior researcher of the National Council of Scientific and Technical Research. He has been director of the Institute of Automatics of the Faculty of Engineering of the National University of San Juan from 2008 to 2019. In 2012, under his management, the institute was recognized as a dual dependency unit National University of San Juan and CONICET. Dr. Carelli has taught numerous graduate courses both at his university and at foreign universities as visiting professor. He has also advised 25 doctoral theses and 13 master's theses and directed numerous researchers. He has given invited lectures at foreign university and at relevant national and international conferences. He has given guest lectures at foreign universities and at relevant national and international congresses. He has more than 115 publications in international journals. Dr. Carelli is a senior member of IEEE and a life member of the Argentine Association of Automatic Control. He is currently a senior researcher hired by CONICET. His areas of interest are robot control, manufacturing system, adaptive control, and artificial intelligence techniques applied to automatic control. So, Professor Carelli, please be welcome to our seminar, and thank you very much for joining us.
Thank you very much, Sergio, for your presentation introduction. But how can I upload my? I have not the command to upload it.
There is a small icon in the right side of the microphone symbol.
Okay. Yes. Okay. So please let me know if you can see the slides.
Yes, we are seeing them.
Okay. Thank you very much. Well, I will give a general presentation of our Institute of Automatics. Not directly related to COVID, but the general lines of research, and then we are going to present our results on the COVID project. Well, our group related to COVIBOT project belongs to the Institute of Automatics, which has a double dependency of the National University of San Juan, Argentina, and of the National Research Council, CONICET, Argentina. San Juan City is located, as you can see in this map, in the center west of Argentina, close to the Andes Mountains. And the scope of our institute in general is research and development, technology transfer, and human resources in the area of automatic control. We have also a postgraduate program in control system engineering, specifically in this area, and with the diplomas of PhD and master. To have an idea of this group, Institute of Automatic is composed of 26 researchers, most of them with full-time dedication. Of course, also includes engineers, technicians, and administratives. And we have currently 22 postgraduate students developing or working on their thesis. The research lines at our institute are industrial automation, process control, robotics, precise agriculture, and in general sensors and applications. And now specifically regarding the group involved in this COVIBOT project, it is composed by the here listed researchers. We are 4 researchers working in this project specifically. And our current work is related to robot manipulators control, which includes advanced, robust, adaptive, and intelligent control. Also, the control of mobile robots and also mobile manipulator robots with mapping and localization, trajectory and path control, cooperative control, sensor-based control, and advanced control applied to these kind of robots. And finally, also, we have some lines, specifically application lines in the robotic area, which includes precision agriculture, assistant robotics, environmental surveying, and also social human-robot interaction. And here I would like to show some images related to our current research line, not including specifically the research in the COVID area, which will be presented later. One of our research lines, as I told you, is the precision agriculture, and in this area we work applying robots also, ground and aerial robots, and also, as you can see, we have developed a robotic arm which is mounted on a ground robot, and it is applied for precise pesticide spraying, which is adaptive, an adaptive arm to the fruit trees canopy geometry. No, so it is a development in the area of precision agriculture. We have also worked intensively in mapping in agricultural environments, applying deterministic mappings for the trees location, which are working with fruit trees, for example, olive trees. And also we have developed some techniques for probabilistic mapping to include moving objects, for example, machines, or even workers in the field, which are mapped to assist in the design of the automatic control of the robots acting in the field area. Another research line is assistive robotics, and in this sense, we are working on the control of smart canes and smart walkers for motion, also cognitive and sensorial assistance. Also, we have the lines of control of mobile manipulators, including ground robots, mobile manipulators, and also aerial mobile manipulators. And these are some of the equipment we have developed. And we are also working with the control of autonomous boats for dam inspections. here, finally, I can say that this specific group involved in COVIBOT project is also working currently in the formation control of robots, in this case multiple drones, to for load transportation, and finally also we work in social human-robot interaction, which includes the social spaces and social dynamics for users' comfort. So as you can see, all these lines are not directly related to the COVIBOT project, which will be explained later, but are lines that aid us in the developments related to the COVIBOT project. So this is all my presentation, so thanks very much for your attention.
Thank you very much, Professor Ricardo. Very interesting, the projects that you are developing at the Automatic Institute in Argentina. Now I'm going to introduce the talk of Professor Carlos Cifuentes from Colombian School of Engineering. So let me read his profile. Dr. Carlos Cifuentes has been a professor with the Department of Biomedical Engineering and head of Center for Biomechatronics at Colombian School of Engineering, Julio Garavito. Since 2016, he has been visiting professor at the Universidad Federal do Espírito Santo, Plymouth University, and EPF Graduate School of Engineering. Before that, he was a postdoc at Universidad Federal do Espírito Santo, Brazil. He received the bachelor degree in electronic engineering from the Colombian School of Engineering. He received his specialization in project management in 2006 at the same university. In 2011, he obtained his master's degree in biomedical engineering from Universidad Nacional de Entre Ríos, Argentina. In 2012, he joined the Robotics and Industrial Automation Group at the Universidad Federal do Espírito Santo to pursue a postdoc degree, a PhD degree. He developed a part of his thesis at Automation Institute and at the Neural and Cognitive Engineering Group in Spain. In 2017, his work was lauded as one of the 5 history-changing ideas in Latin America by History Channel. In 2020, he was elevated to the grade of EEE senior member. This year, he was appointed as associate editor for EEE Robotics and Automation magazine. His research on human-robot interaction is world-leading, and his team research has conclusively shown the benefits of using robots in healthcare contexts. Funding agencies such as the Royal Academy of Engineering, Ibero-American Program on Science and Technology for Development, and Ministry of Science, Technology and Innovation in Colombia present his research as funding success. So, Professor Carlos, welcome to the event, and thank you very much for joining us today.
Thank you, Sergio. Can you hear me well?
Yes, and we are seeing your screen.
Great, great. Thank you very much for all the researchers, the professors coming today to this meeting. We would like to do personally, but of course, this project is about the pandemic, so it's the way to do the research during this time. We expect that next year will be more in touch, more personally, but I think we did a great job during this year working in this project. This is also a very short project, this 1 year and a couple of months project. But the idea was like that, create a network, work remotely, interact, and find ways to support the pandemic with our experience, with our previous work. So now in the next talks, we will see more of the results that we have done with the collaboration of the international professors and our students. But in this time, I will show you a bit about our group, our university. So we started with this project of a Center for Biomechatronics in 2016, which belongs to the Biomedical Engineering Program and at the Colombian School of Engineering. And in that time, we started to create strong partnerships with clinicians, with healthcare institutions, and in that way, we started to identify the necessities and the opportunities to develop technology to support the healthcare systems and also the patients in the treatments. And in that way, we propose relevant parameters or robot behaviors that can support or can help patients in long-term treatments. And we usually apply this methodology in every case study that we are working with the clinics. So our research is very practical. So we are trying to find real problems, and from these problems we try to apply the state of art of the robotics and technology in general. And the way that we materialize that is through studies. We perform usability tests, short-term use studies, and long-term validation. This is our methodology, and in these videos we can see a short summary of our works. We have mainly, even before the pandemic, we had 3 lines: robotics for cognitive support, robotics for physical assistance, and affordable robotics. Some of these videos are before the pandemic, so maybe you can see some patients without the mask, but some of them are during this year, during the last time, and we can see all the safety measurements. And in the part of robotics for cognitive support, the idea is to develop robotic assistants, robotics companions that can support patients in long-term treatments, applications in treatment of autism, in general neurodiversity. And for instance, you can see this robot, Castor robot, in the top left part. This robot was developed by a collaboration also with UK in another project. In this part, we developed an open source robot that we are deploying in different rehabilitation centers and universities to develop this kind of studies. But you can see one of our last words is we are studying how this robot can be applied in affective therapy. So you can see one of our students hugging the robot, and we are evaluating this concept to transfer to other healthcare applications like older people care or people with necessities of affection. That is also a huge issue during the pandemic because the isolation of the people. So robots can help a lot in the disinfection and in the management of a lot of application that we have seen today, but also in therapy in affection, which is also important. We are also done some work before bringing robots to the clinics, trying to support in some tasks. That you can see also in the left part of the presentation. You can see now robot supporting patients in neurological treatment and also in cardiac rehabilitation. And those projects we have the opportunity to see later. Sergio will show us a summary of this project because we had this project before the pandemic, but we had to deal with the pandemic to finish the studies, and it changed a lot the interaction. And also we did a perception study with the clinicians because before the pandemic they were quite afraid to the replacement of the robots, but after the pandemic or during the pandemic they expressed the interest to have the robots also to avoid physical contact with humans, with patients, and also try to use in a remote way to command the therapies. So this is also another output of this project. We have the opportunity to see later in the Sergio's presentation. And the other line of the work is robotics for physical assistance. This is not very linked with the project because in that way it's more support patients in the mobility, in the daily life tasks. So you can see different applications of robots can support people that usually use a wheelchair or something like that, or they are under long-term rehabilitation treatment. So you can see some videos that we had some about our platforms, also a lot of work in navigation. That it was a great input for this project because in that way that automatized different tasks like sterilization or cleaning or disinfection. This navigation part is very relevant at this point. So this previous experience in mobility assistance was very helpful for this project. We also, before the pandemic, we were working in developing modular assisted robotic devices. You can see in the bottom part in the middle, an hand exoskeleton and an ankle exoskeleton. And these models are come from this methodology that we saw before. We found the necessities in the clinics to perform this kind of therapy and the necessities in our Latin American countries or developing countries to have this kind of technology. So we work on these exoskeletons, and the good thing is that it is being used in clinics around Latin America at this time, and we are integrating with several technologies like EEG, DCI, or serious games to encourage people to do rehabilitation. It has been also a nice experience to discuss how has been the use of that during this time, that it implies the contact or the recruiting of patients. And those patients are also under complicated situation because they will have more comorbidities around the COVID-19. So we have been struggling to manage these studies, but it also has been very interesting to understand how to use that for this pandemic or future pandemics that it may happen. No? In the left part, we have some projects that are related to the others, but in that part, we are more focused in develop the device itself and instead of develop the treatments or the rehabilitation with robotics. Here we are looking for the deployment of the device. So this exoskeleton and also this prosthetic hand was developed using soft robotics, tendon driving systems, and we have been working in transfer this to a real application. So the exoskeleton is now open source. It has been used in many places, and the prosthetic hands, we recently tested with a patient in Medellin, and was very interesting. The performance of this prosthetic. It brought a lot of attention from the media, and now we are seeing how transfer to the company that is involved in this work. Actually, we don't have a lot of experience in hands prosthetics, but it has been a nice application of the other technologies that we have been developing in the group. And the last part is some of the results of the COVIBOT project. You can see the robot navigating in our building, disinfecting. We'll have the full opportunity today to hear how this robot can do that and how we are planning to deploy that in the university. We are expecting next year the full capacity of the university with all the students and professors. So we are trying to that solution that we'll see today become real to be used in that moment. You will see some nice outputs that we had from this project, and it was really good support from the Royal Academy to center this knowledge in this application that we can use in our daily life, which is the university. So most of the work most of the output that we have today are real applications that will help us. We are most of the time thinking how to support patients and healthcare system, but with the solution that we will see today about the COVIBOT project are very related to our lives, how we will manage when we will be in the university next year. Even though we are going to the university right now, as part of our students are going to the labs and doing practical work of the subjects, but the next year we'll expect to have full capacity. It also will be a matter of discussion, because in UK, Professor Suramania can say how is now, because I think they are in full capacity now in the university. So we are preparing to that, because the pandemic, the COVID-19 is still in our lives, and we have to be careful and learn from the experience. And also there is another work with social robots that Daniel will have the opportunity to show us an interesting application, how robots can support us to encourage us to keep the biosafety rules. So this is the general idea of our work. Of course, we have done this with a lot of support of healthcare institutions. We have here a summary, but there are some missing of institutions in Colombia and Latin America and around the world, and some companies that has trust in us to develop those projects in Colombia, and also one company from UK and one company from the US. And a lot of universities are research centers in Latin America, US, Europe, UK, has been very helpful for our research in the context of Latin America or developing countries. So thank you very much. We'll have more time in the end of the meeting today to discuss or to resolve any doubts presented today. Thank you, Sergio, also for managing this wonderful event.
Okay, thank you, Professor Carlos, for your presentation. Very interesting, all of the research lines that you have in your lab. So now we will continue with our schedule with Felipe Ballén. Felipe Ballén is a mechanical engineer from the Colombian School of Engineering Julio Garavito and obtained his master's degree in electronic engineering with emphasis in biomedical engineering from the same university. His interests include biomechanical analysis and kinematics of human-robot systems, mechanical design, prototyping techniques, and additive manufacturing. He has published his work in different congresses, conferences, and journals. In this talk, he will present a passive disinfection platform that was developed by students and professors of the Biomechatronics Center of the Colombian School of Engineering Julio Garavito. The platform consists of a UV lamp and an automation system for disinfection tasks. So, Felipe Ballén, please be welcome to this event, and thank you for joining us today.
Thanks, Sergio. Happy to be here to share all our advances in this project. So let me share on my screen. Let me know if you see my screen, please.
Yes.
Okay, perfect. So today I will speak about the mobile platform from disinfection advances. So first of all, I will explain the problematic state-of-the-art different phases that we achieved during this process. So as we know, the main problematic after the quarantine period, we are resuming our activities in order to reduce the transmission, the rapid transmission of COVID-19. But during gradually, we are going back to our activities. We need to disinfect the surfaces and enclosed spaces the fast and the most practical way as possible. So as we know, we have, if we are in an enclosed space, we are in danger to gain that the COVID-19. So in this part, I will focus in the disinfection systems and which disinfection systems are and which ones are the common way. So the first type of disinfection and the most common that we found in the literature are the UVC lamps. So these lamps basically provide an specific radiation that destroys the main protein that the coronavirus sticks into our body. So these lamps are widely used in clinical environments because of the effectively function as germicide lamps. So that is the first disinfection system that I wanted to talk about. The second one is a more common disinfection method that is basically spraying sodium hypochlorite. Basically, this type of disinfection is more common and allows a low cost, and all of us we are doing in our homes and the beginning of the pandemic. So different health institutions starts to put some guidelines according to this how to use this disinfection according to a solution concentration that can be used in different environments. So in common environments, we can use this solution concentration at 5%. So using these disinfection systems, in the market are too many robotic devices, most common in US and Europe. But most of these disinfection systems, as you see in here, there are three main examples. Most of these robotic systems are very expensive. So our task during this project are basically to how we have to develop a low-cost disinfection model for robotic platforms. So first of all, as I saw in the state of the art and the problematic, we identified the principal components, the mechanical and electronic components. Then, according to this, we perform a selection of materials and which are the functionalities, the main functionalities that we had to take into account in order to achieve a proper disinfection model. So the three main results that we achieved during this project was the first one, the disinfection spray model using the sodium hypochlorite. Then disinfection model based on UVC radiation, and the third one is the integration model. So we have these two models, but we need an interface in order to command them very well. So this is an overall scheme of the mechatronic development that we established. So first of all, in the left side, we design a spray model. So basically, we integrate different commercial products in order to achieve this spray model. So as I told you, we are going to use this hypochlorite as a disinfection. Then we use a pump that works at 12 volts and 6 amps, and spray nozzles that we also select them because of the volume that it covers using this framing system. And then we also design a mechanical structure that is based on 3D printing. Then on the right side, we also design a UVC model. So in this part, we have a product that is already tested, that is basically a UVC lamp. As I told you previously, this UVC lamp is already on a product, and we only just adjust this product using a power inverter in order to use the final interaction model that basically is a Raspberry Pi and an activation model that is linked to a battery, and then using a smartphone and a user interface, the user can use these two models very easily. So this is the disinfection spraying model. So as you see, we select different materials. In this case, the 3D printing material was ABS because according to our disinfectant, we need to avoid that the material degrades during the time. So the ABS is the best selection for us. Then the ubication of the nozzle sprays is also thinking of how to cover the more volume in order to disinfect more and better the wide spaces. So, and then the next part is the UVC model. As I told you, we already bought this the UVC lamp, and we also bought this specific UVC lamp because it has a maximum coverage area of 40 meters squared. And as I maybe told previously, this destroys the protein, right? But we also combine these two types of disinfection because using this UVC, we don't use this type of disinfection system because it's kind of dangerous for the person. So we combine these two ways to disinfect in order to achieve and continually disinfect the spaces around us. And then the user interface. So basically, as I told you, so we have the spray model. So it's just like we can activate or deactivate these models according to a user interface that anyone in our phone can use. So that is like the practical way. that in this part of this model is very important because most of the users will have a smartphone. So that is like the main tool in order to command this this product. So this is the main prototype. This prototype is already, it is the first prototype that we built. And we also have a little testing over here. So so in this part, we already test this prototype with the janitors of the university. So basically, this is one of our researchers that is explaining to the janitor how to use the device. And as I told you, only using the smartphone, we can activate and deactivate each model. So this is the first model that the generator is just activating that and deactivating the sprite model. So in this part, as you see here, we can as you see here, or the generator is already activating the sprite model remotely. So that is the first part that is very important because most of the the next disinfection system is very important that most of the person that is using the UVC lamp will be farther away. Okay, in this part we are explaining that how it works the UVC model, right? So basically, these lamps just they're in a specific environment. They put it in their room or the place that we want to disinfect, and start the disinfection. So depending of the area and of the room and this time can vary between 20 to 30 minutes. And as I told you, the janitor can activate and deactivate this model in case of, I don't know, anyone entered to the room and didn't notice that the UVC lamp was turned on. So that is the very interesting functionality that we considered during this project. So the main conclusions that we came with during this phase of this project that we identified different low-cost components that allowed us to develop a disinfection platform, right? And we also developed a mobile user interface in order to command this product. Another interesting part is that we made a partnership with a company that you see in here that is Mobiline, sorry, and in order to enhance this prototype and convert them to an industrial product that most of the other companies or university can buy in order to protect our community. Another big conclusion is we are building 3 prototypes in order to deploy them to our college because as Professor Carlos said previously, in the next semester we are coming back fully, so we need to guarantee to all the community be safe and keep disinfecting these spaces. This is one of the advance of the company during this process in order to pass this prototype to a real product. So we are pretty happy because we are going to see that the research that we did is going to have a high impact in our community, either in our universities or companies that will use this product. So the ongoing work that we are done and that we see in the next presentation is that, okay, we already have the different models to disinfect the spaces, but we need to understand how to navigate during these different environments. So that will be explained for my colleagues. So thank you very much for turning on this presentation. And as you all know, if you have any questions, you can do it in the Q&A section.
Okay, thank you very much, Felipe, for your presentation. Very interesting, this module of the COVIBOT project. So now we will continue with the presentation of the smart rooms and autonomous navigation system. This presentation is going to be performed by Luis Arciniegas and by me. Luis Arciniegas is a research associated to the Colombian School of Engineering Julio Garavito. In 2015, he received his bachelor degree from the Electrical Engineering program. Subsequently, in 2020, he received his master's in biomedical engineering from the biomedical department of the Universidad del Rosario and the Colombian School of Engineering Julio Garavito. From 2018 to 2021, he has been working in the Center for Biomechatronics in Rehabilitation Robotics, applying physical human-robot interaction strategies in a lower limb exoskeletons control architecture. His primary research interests are the lower limb rehabilitation robotics, wearable robots, and the development of control strategies for prosthesis and orthosis. So, Luis Arciniegas, welcome to the event and thank you for joining us today. You are mute.
Okay. Hello? Yes.
Yes.
Okay, thank you for this presentation, Sergio. And now I am going to share my screen to start with the presentation. Okay, just give me a second, please. Okay, can you see my screen now?
Yes.
Okay, let's start with this.
Okay, so I will start the first part of the presentation explaining you all the navigation system for disinfection processes. So as Felipe Allen explained, we already have a disinfection platform, which is passive. And the idea now is to make it robotic and autonomous for disinfection tasks in our university. At this point, we found ourselves with three main problematics. The first one is how to perform autonomous navigation in an indoor setting. The second one is how we can configure the robot to perform simultaneous localization and mapping. And finally, how we can execute path planning and path solving routines. So to address this problematic, please next slide. We have been using the ROS navigation stack. ROS is the robotic operating system, which is an already built-in framework to develop software for different kind of robots. And particularly in mobile robots, they already have this navigation system that comes with all of the models that solve this problematic that I was talking about. So just to give some details about the navigation stack, this is the main network of the navigation stack setup. It gathers information from the sensors, sources of the road, for example, from the surrounding obstacles, from the images of the surrounding surroundings of the road. Then it also gathers information from the odometry source. It collects information from the motion of the device, and it also has information from the map of the environment where we are going to interact with the road. With all of this information, it has several planners to perform SLAM, which is simultaneous localization and mapping, and path planning and execution. So at the end, it sends the velocity commands to the robot to move it from one point to another in a safe and efficient way. So to implement this, we use the Pioneer LX robot, where we have already developed some simultaneous and localization mapping tasks, as you can see in the gray images in the center of the slide. And we have also tested the path planning and execution system. At this point, there are some unsolved questions, which are how we can address multi-story buildings. For example, here in the university, we work in a building with third floors. So if we want to send the robot from one floor to another, we need to approach, for example, doors opening and elevators interaction. However, within the scope of this project, these two questions are not going to be solved, just to clarify. So our research question is basically focused on determining what are those implications of implementing the ROS navigation system for automated navigation and disinfection tasks. For the methodology, so we select a particularly mobile robot with all the sensors and actuators already built in. We configure the navigation stack and develop a scheduling application to prioritize the different disinfection tasks, as Luis is going to explain later. And we also develop several disinfection and cleaning routines, and finally test the navigation system. As for the results, we implemented all of these, as you can see in the robot in the left side of the slide, and we implemented the navigation system in a cloud architecture. As you may imagine, this kind of software might be computationally expensive. So we use a local server in our university using a particularly configured CPU, and this server communicates with the robot and send only the navigation commands and retrieves from the robot the information from the sensors. As you can see in the right side of the slide, we also develop some cleaning routines. This basically means once the robot is in the room that is going to be disinfected, how we address the disinfection. We simply place the robot in the center of the room, or we perform a zigzag routine or a circular routine or a square shape routine. So we develop several routines to compare them. Prior to implementing this in a real environment, we perform a simulation using Gazebo and ROS. So as you can see in the left side, we design a simple environment emulating what will be like, for example, a university floor. And we configure the navigation to go to the different rooms in the environment. So as you can see in the GIF, the robot is disinfecting, and in blue, you can see the zones that the UV disinfection is reaching. And finally, we did a case study with the real robot. So as you can see here, the robot is disinfecting two different scenarios. In the first one, is performing a simple routine. It enters the room, it goes to the end of the room and goes back and exits the room. And in the right side, you are seeing the robot disinfecting a particular environment, performing one of the routines that we designed. So now Luis is going to explain you the smart rooms models that couples with the navigation system.
Okay, thank you, Sergio. With the purpose to complement the navigation system that Sergio presented in the previously slides, is required to estimate which rooms need or don't need to apply the disinfection process, right? With this purpose, it's necessary to develop one algorithm to classify or to assign priority level for each rooms in indoor environments to decide which room is the new goal to the disinfection robot, and the disinfection robot make a trajectory to go to this room. For this purpose is identify three problematics. The first is identify and monitor the parameters that increase the transmission risk for COVID-19. The second is an score estimation or assign a score estimation for rooms according to the selected parameters. And finally, determine the disinfection priority based on a score assigned to each room according to the monitoring parameters. In this sense, is generated the research question that is what would be the decision-making system that could be applied in the environment disinfection prioritization for the prevention of SARS-2 COVID-19 virus. In the state of the art, we can found different strategies to classify or to prioritize different tasks in different areas, and not only in this case that we are trying to classify the rooms that need or don't need to apply the disinfection process, right? In this case, we found a decision trees method, priority-based message methods, a first come first served methods, and shorted just first methods, right? Some of these only, for example, select one task and depends, for example, that in the order that the task is registered or assigned in the CPIU, in the same order is attended or is resolved this task ready. And another example is, for example, in the shorter job phrase is, in this case, we have 3 tasks and the computer select the task that the solution is really short or is the easiest easiest way to resolve, right? In this case, we have we have a general schematic that describes what is the main purpose with this project, right? In this case, we divide in 3 main modules that is involved in this project of the smart rooms. The first is the priority parameters scores that define or apply the making decision process, where select which rooms in an indoor environment needs or don't needs, or in which time need the disinfection to apply the disinfection process, and it is located in a server, right? The second is a Markov chain disinfection robot. It represents is the representation of the disinfection robot in a mathematical formula or equation, right? And it represents different states that the disinfection robot could be present in different times, right? As an example, the disinfection robot could be in transit in transit in a room to apply the disinfection process, or a state that the disinfection robot apply the disinfection methods to disinfect the rooms, right? And finally, we have a Markov chain room that is the equation that represents each room in an indoor environments that in this case is each room present different states according if the room is disinfected or is in queue to apply to the disinfection process by the disinfection robot, right? In this part, the first module that we mentioned is the priority parameters score. That in this case we applied a Markov chain, Markov making decision process to develop this process, and in this case we have a first schematic where we have a room. In this case is the room in an indoor environment that for each room is quite different parameters that with these parameters the robot can estimate if the room needs or don't needs them to apply the disinfection process in X or G time, right? In this sense, the literature shows that different parameters, in this case, the number of persons in the room, the CO2 levels, the time of the last disinfection, and others generated by the people don't use the mask in your face is required to estimate if in this room is presented a high risk or high levels to infection to COVID-19, right? The second and the third module it was composed with the same method. In this case, is used a Markov chain hidden method for the disinfection robot and the room. And to define these equations is applied a model simulation that is applied using 10 million iterations when in each iteration is equal to 1 minute. The CO2 levels is acquired or estimated for each minute. The number of persons of the room is acquired or uploaded every 5 minutes, and the length of the class is equal or is uploaded each 150 minutes. Additionally, is taken into account some properties to the robot. In this case, is taken account the battery or the robot battery. And according to the literature, the disinfection time is approximately 50 minutes, and one additional state that is taken into account the parameters evaluation that I mentioned in the last slide is 10 minutes. As a result, we have two Markov chains methods applying to the robot and the room presented in these state machines with different state for the robot and for state for the room according to if the room is in disinfection process or is simply to the robot to apply the disinfection process. At the same time, in the robot is presented different states. In this case, when the robot is in transit to the room to apply the disinfection process, or is available to, or is already to start to work, right? Finally, we established some parameters to estimate the risk of COVID-19 infection in rooms. Second, is assigned a grade or a level to prioritize each room using different parameters to identify the risk of COVID-19. Finally, we have we organize each rooms according to a prioritization level to execution of the disinfection process in each room. And finally, the room and the disinfection robot were designed such as a state machine for the development of the disinfection process in the room environments. And now we are working in the instrumentation of our lab to apply the smart rooms, acquiring different parameters that I mentioned in the last slides. For example, the CO2 levels, the number of persons in the classroom, or if the people have or don't have the mask in your face. Thank you so much, and I am ready for any question if you have some questions.
Okay, thank you very much, Luis, for your presentation. Very interesting, all of the developments that you're working on. So now we're going to continue with the presentation of Daniel Garcia. He is going to talk about a mask detection system using a social robot agent. Daniel is a student of the program of biomedical engineering at the Colombian School of Engineering Julio Garavito. He has been working since 2 years now in the laboratory of the Center of Biomechatronics at the Colombian School of Engineering, and he has also published some parts of his work in several conferences, and journals. So, Daniel, please be welcome to our event, and thank you for joining us today.
Thank you, Sergio, for introducing myself. I'm going to share my screen. Are you using my screen?
Yes.
Yes.
Thank you. Okay. Hello, everyone. As Sergio said, My name is Daniel Garcia. I'm currently an undergraduate student of medical engineering. And today I'm going to show you the preliminary results of the evaluation of a social robot as a mechanism of control and monitoring of the correct use of a face mask in public spaces. Okay, today's agenda is as follows. I will talk a little bit about the issues and the motivation for this project. Then I tell you about the alternatives that are currently being implemented for monitoring the use of a face mask. After that, I will present the methodology that we followed to validate the system that we are proposing, and the preliminary results that we obtain, and the conclusions. Okay, the main motivation of this project is COVID-19, a highly infectious disease that can cause several respiratory problems. Thanks to this disease, according to the World Health Organization, more than 4 million deaths have confirmed worldwide, and more than 200 million people have been infected. Specifically in Colombia, according to reports from the Ministry of Health and National Health Institute, more than 4 million cases, approximately 126,000 deaths have been confirmed. For the reason, the mask is one of the most important methods to minimize the spread of the virus. Okay, thus many multidisciplinary teams have started to work on the proposal of different strategies for the monitoring and control of the use of the mask. One of the most important is the use of artificial intelligence algorithms. These kind of models, after being trained, are able to make a decision by themselves according to the problems for which they were designed. In this specific case, they can decide whether a person is wearing a mask. For this purpose, different object detection methods and different machine learning libraries have been implemented. However, as we can see, many of these developments are limited to static and controlled tests, and those models are that are validated in a dynamic environment, which are very limited, do not provide any feedback to the users. Okay, for this reason, different strategies have emerged to overcome this limitation. Drones are one of them. However, as the size of these devices increase, the battery life is considerably reduced, which can be dangerous in public spaces. And in addition, in many countries, license and special permit are required to use them. The screen and speakers are another alternative, but due to their low interaction with the users, in many cases they are ignored. Finally, one of the most attractive and little explored strategies in social robotics is the social robotics. In multiple studies, it has been demonstrated how these robots are able to interact with the people, and in some cases provide some kind of feedback to the user on the task being performed. To further understand the versatility of social robots, I will discuss 4 studies reported in the literature that provide evidence of the importance of this device. In this work, they were interested in seeing how the people change their behavior when they observe a robot or a person performing a task. Specifically, they studied the influence of watching a robot or a human picking up, discarding garbage on the observer's willingness to throw away to pick up garbage. The study was conducted as a video-based survey. At the end, it was found that the people who watched the robot video were more willing to throw away or pick up the trash, and those who watched the human video. In the second study, people motivation when exercising was assessed. The study was divided into two groups. In the first one, the exercise session was led by a person. In the second one, it was led by a robot. In the end of this study, it was concluded that those who were led by the robot were more motivated when exercising. In the third study, the motivation of a group of children was evaluated when they were studying. One group had to do their work without any help, and the second group was accompanied by the social robot. These images speak for themselves. The children who were alone after 10 minutes completely lost motivation, while the group that was accompanied by the robot managed to successfully complete the task. And finally, this study showed how the people feel more motivated with a social robot than with an intelligent computer when it asks them question of find out how they feel about their health. With this in mind, we propose the following research question in order to validate the system suggested system. Can a social robot function as a mechanism to control and monitor the correct use of face mask? To achieve this, a first stage is proposed where the operation of the system is validated by the video. This has objective of providing information about people's perception. In the video, four possible situations are presented. In the first one, the user is wearing the mask correctly and the robot provides a comment, no? The second one, the user is not wearing the mask correctly and the robot provides a comment and the user performs an action. In the third one, the user does not have the mask and the robot provides a comment and the user performs an action. And finally, a situation presented where the user simulate having the mask on with this hand or with his shirt, as we are going to see. And the robot managed to detect when the user has the mask or not correctly. After watching the video, the person have to complete the standardized ghost speed survey. Okay, and this is the questionnaire. Basically, it consists of evaluate 5 categories: anthropomorphism, animacy, likability, perceived intelligence, and perceived safety. Each category has a certain number of questions, and each is answered on a Likert scale of 1 to 5, where 1 is the lowest score and 5 is the highest. Okay, the second stage is an evaluation with the robot and the system running in a real time. Basically, the perform must enter the building and interact naturally with the robot. When the robot detects the correct use of the mask, it gives positive feedback, and when it does not detect the correct use of mask, it gives corrective feedback. Finally, the data obtained into the group were compared. For this purpose, the Mann-Whitney-Wilcoxon test was used to determine if there were significant differences. As for the results, 3 cases in the university's test were detected. The first referred to a person who entered with the mask incorrectly and robot provided positive feedback. The second, the person entered without the mask and the robot provide a corrective comment and the user perform an action accordingly. And the last one, the person who entered with the wrong mask on, as in the previous case, the robot provide a corrective comment. The subject perform a corresponding action. Finally, it's important to highlight that the research in charge of the study provide a brief explanation of the study to the subject that when interacted with the robot, we would give him a comment, and he should perform an action he believed to be correct. Okay, as for the results of a survey for the university test, we have 50 participants, of which 28 were males and 22 were females, with an average age of 21 years. For the test conducted in Google Forms, we achieved 192 participants, where 133 were males and 59 were females, with an average age of 25 years. For the test conducted in Google Forms, just in a video experience, we, in terms of perceived intelligence, the group that performed this validation present better results. This may be related to the fact that the participant in this stage had the possibility of seeing all possibilities situations regarding to the use of the mask. Specifically, the last situation and the last video that we've seen, where one of the researchers tried to simulate that they have the mask with his hand, and the robot did not say that the subject had it. In the image, we can see the distribution of response by the participants. Among the most relevant results, it can be seen that in general there was a positive distribution of the answers. Regarding anthropomorphism, animacy and liquidity, besides presenting a statistical difference between the two stages, the group that took the test in the university present better results. This may be related to the fact and by interacting directly with the system, users were able to better perceive the system behavior and have a better approach. Finally, the group that test with the video presented better results. The results tell us that possibly the people who interact with the robot at the university identified certain situations that did not allow them to feel completely safe with the device. However, as we can see, the results in both cases present positive distribution. And finally, the conclusions, the University Validation Group had a better perception of the human behavior of the system due to the direct interaction with the system. No? Another conclusion that we have is the survey validation group presented better results in the perceived intelligence since they had opportunity to see more possible situations regarding the use of the face mask. And finally, the results suggest that the proposed system is a potential tool for monitoring and controlling the use of face mask. Thank you.
Okay, Daniel, thank you so much for your presentation related to the mask detection system. And let's continue with the next project related to the clinical case studies that is presented with Sergio Sierra. Sergio Sierra is a professor and researcher at the Biomechatronics Center of the Colombian School of Engineering, Julio Garavito University. In 2017, he graduated from the Biomedical Engineering program of the school and the Universidad del Rosario. With this thesis focused on the development of a navigation interface for a robotic walker. In 2018, he joined the master program in electronic engineering at the school and the development part of this thesis at the Federal University of Espírito Santo in Brazil and the Institute of Automatics at the University of San Juan in Argentina. He has participated in different research projects and networks in the last 3 years. His main research interests are related to the rehabilitation and assistive robotics, physical and cognitive human-robot interaction, control systems, advanced sensor processing algorithms, and machine learning techniques.
Okay, thank you, Luis, for introducing me. I'm going to share my screen. Please confirm me if you are already watching it.
Yeah.
Okay, so today I'm going to be talking about the clinical context of our project. So as we have already seen in the previous presentation, we have already talked about the disinfection robot, for example, that works in cooperation with the smart rooms model and the navigation system. And we have also made some tests integrating these models in a laboratory and control context. Now, the idea is to analyze what will be the effects of deploying this kind of technology in a clinical scenario. We are basically asking ourselves if the clinical, if the clinicians are going to accept this kind of technology, will they adopt this technology, and what effects is going to have in this scenario. So as we have already talked in the previous presentation, I'm not going to extend myself in this slide. Technology has been a major character in the managing of the pandemic effects since the COVID-19 outbreak, and we have seen some of the different fields that technology might help us in this process. Particularly for this presentation, I would like you to focus on 3 types of robots, which are on the left side, disinfection devices that are able to automate disinfection routines in hazardous and dangerous environments. Also, service and logistic robots that are the devices that have been widely used in the industry, and now they're being used in clinical environments, for example, for food and medication delivery, and also telepresence and social devices, as we are seeing in the right side of the slide, which are robots that promote the patient to clinician communication and promote social distance as they maintain this communication in a proper way. So keeping in mind these three kinds of devices, we ask ourselves, what are the perception and expectations of the clinicians about these kind of robots? We would like to know if they found them useful, if they find them safe and appropriate for their daily activities. So for this study, we applied a quantitative study, a quantitative methodology, where we gathered 41 participants, all of them related to the healthcare context, and the majority of them with daily work activities related to COVID-19. And we proposed a questionnaire based on the following constructs. The first one was knowledge. We formulated questions related to determine how much the clinicians know about robotics in general, and what are their experience in using these kind of robots, for example, disinfection assistants and telepresence devices. The second category of questions was focused on determining how was the attitude of these professionals about these devices. We would like to know if they found them useful, if they like them, this kind of technology, and if they believe that they are able to mitigate the effects of the pandemic in their daily activities. And finally, we ask them how they use these kind of devices in their daily activities in a real scenario. We would like to know if in their daily job they really use these devices. So for the results of this part, we found something very interesting. As you can see in this part, in the knowledge category, the majority of the question had a negative distribution. This means that the clinical professionals don't believe that they have the enough experience about these kind of devices, although there is a slightly positive distribution related to robotics in general. However, regarding the attitude of these participants towards this kind of technology, we found a very positive attitude towards these devices. So this is very promising, because these tell us that if we deploy our technology and the technology that are developing our partners, they are going to accept them in their daily activities. And finally, and this is a sad result, we found that in practice, in real scenarios, they don't use these devices, basically because the institution where they work don't have the capacity or don't have the interest to acquire this kind of technology. Then we ask them some open questions. We would like to know, in their opinions, what are those key functionalities that a disinfection assistant and telemedicine robot should have. As a common denominator, and as we can see here in this picture, the majority of the participants answered that these devices should be safe, they should be user-friendly, and they should provide a precise interaction. This focus, for example, in disinfection, means that they want the robot to actually disinfect the environment, focusing, for example, in the assistance and service roles. This means that the robot actually helps them in their daily activities, managing the patients, and provide, for example, alerts when there is a hazardous situation with the patient. And finally, the most important thing with the telepresence devices is that they want the robot to provide a proper communication and interaction with the patient. So for this study, we found three main conclusions. At first, although the knowledge and practice scores were low, as we saw in the results, there is a positive attitude toward robotics for COVID-19 in the medical community. So this is very important because, as I already told you, this might induce us to think that they are going to accept and adopt properly the technology that we're working on. However, talking with these professionals, we identify also that that there is a fear that is remnant in the medical community because they fear that the robot might replace them. However, if the activities that the robot are going to replace, let's say, are repetitive tasks and tasks such as food delivering or toileting tasks that they categorize as boring or not that important, this fear is irrelevant for them. And finally, in the Colombian context, we found that the majority of the participants indicate a positive perception about the ability of Colombian groups to develop this kind of technology. So this is also a very promising result. And also to show you another study where we actually deploy a social robot in a clinical environment, I would like to introduce what we call the social robots, such as the one that Daniel was presenting you in the previous slides. So it is a matter of fact and something that has been already evidenced in literature that social robots are useful for promoting several issues interacting with patients and with other adults. For example, the social robots are very useful to promote mental and physical health, accompanying and coaching patients that, for example, had problems, cardiovascular problems, or patients that live alone in their houses, and those things. Also, there is evidence that the social robots can also relieve the work the healthcare personnel, and this doesn't mean that the robots are going to replace the healthcare personnel, but help them to relieve them from tasks that are repetitive, so they can focus their concentration in other more important tasks. And there are also another capabilities and features that this kind of robot provide that we can discuss maybe later in the question section. So what we wanted to do with this study is we have a social robot, particularly the Now robot, and we want it to be deployed in a neurorehabilitation environment, particularly with the Locomat gait trainer. So our research question here was, what are the effects of a long-term evaluation with a social robot for gait training in neurorehabilitation sessions with Locomat? So this is the setup that we propose. There is in the left side the Locomat, which is a very complex and very useful gait trainer for gait rehabilitation. And the idea is that the robot will be introduced in the therapy as an additional agent to help the therapist to obtain a better performance during the therapy. So in this particular study, there were three main tasks that the social robot was in charge of. The first one was motivation. The robot was in charge of all the time speaking with the patient and motivating him or her to better perform in the rehabilitation session. The second one was monitoring. The social robot was connected to a bunch of sensors that were placed on the patient. For example, IMUs in the head and in the back of the patient, a heart rate sensor, and some other sensors. And if there was a hazardous situation or unhealthy situation with the patient, the robot was in charge of speaking with talking with the patient and giving them feedback to correct such unhealthy situation. For example, in this study, we focus in the posture of the thoracic part of the patients. When they are using this kind of devices, they tend to bend their backs to the front, and as the clinician is focused in other things, sometimes they don't give the proper feedback to the patient. So we propose a methodology consisting of 15 sessions where the participants repetitively assisted to the sessions with the robot, and we also divide the group in two conditions: a control condition and a robot condition, which was the one that was interacting with the robot in the sessions. So regarding the results, we found several promising outcomes. For instance, as you can see in the left side of the slide, this is a distribution of the perception of the patients about the abilities of the device. So you can see in green here that for the majority of the categories, for example, safety, usefulness, and trust, the majority of the answers of the patients were positive. And in the left side, we are seeing a comparison of the thoracic and the back postures of the patients during the session. So as you can see here, for example, in green boxes, the percentage of the time that the patients were having a healthy position was the majority of the times greater compared to the robot. So this is a very promising a very promising result, because this means that the robot actually helps the patients to correct their postures and their unhealthy behaviors during these sessions. So as for the conclusions, as we have already seen, the results show that the posture improves when the robot is assisting the patients. Also, the medical team stated that they benefit from the robot support, as they can focus on other tasks that are more important in the session. And they also highlight that they trust in the system as a complementary tool for rehabilitation. So these are some of the cases where we are actually deploying robots in COVID scenarios, and we are having very positive results with our devices. Thank you very much.
Sergio, sorry, you are mute, and thank you for your talk.
Okay, thank you. Now I'm going to introduce Professor Flavio, which is going to present the advances of the Institute of Automatics. So Professor Flavio Roberti was born in Buenos Aires, Argentina. He graduated in electronic engineering from the National University of San Juan in 2003. And on March 2009, he obtained the PhD degree in Control Systems Engineering at the Instituto of Automática of the National University of San Juan. He is currently professor at the National University of San Juan and researcher of the National Council of Scientific and Technical Research, CONICET. So, Professor Flavio Roberti, please be welcome to our event, and thank you for joining us today.
Thank you very much, Sergio, for your introduction. I'm very glad to be in here in this seminar. I'm going to share my screen now. Please confirm me
yes,
if it is okay. Well, as Sergio says, I will talk about precise robot-based disinfection for COVID-19 prevention. Well, the main objective objective of the work is to disinfect an indoor environment with an autonomous robot equipped with some disinfection devices, and also regulating the intensity of the treatment according to the human access to each area. The contribution of the work can be summarized as you can see in the slide. First, a two-dimensional procedure based on an autonomous vehicle with a fixed disinfection device. This device can be, for example, an UVC lamp or a spraying system. In particular, we consider an UV lamp. Then the consideration of human access frequency in the probabilistic mapping, the definition of an disinfection index. We will see later in this that this index depends on the environment, the human access to each area, and the elapsed time from the last disinfection. Also, the regulation of the disinfection intensity by regulating the autonomous vehicle velocity. And finally, some additional functionalities can be incorporated as obstacle avoidance, sound alarm, or sound alarms, for example. Some previous related works of our group are in the field of robotics for precise agriculture, as Professor Ricardo told you, SLAM and probabilistic mapping, also in agricultural environment. And we have a lot of experience in path planning and path following control. Well, the proposal has three operation phases. SLAM process for map construction and update, including the disinfection intensity function update. The map construction includes both a deterministic map and a probabilistic map. Then a path planning for precise disinfection, and the disinfection process itself, including the deterministic map update and also the disinfection function update. Well, as mentioned before, we use both probabilistic and deterministic map in order to take advantage of the individual benefits of each of one of them. The methodology for the probabilistic map is taken from a previous work of our group, which is included in an issue of the International Journal of Automation and Computing in 2019. But then we have the disinfection intensity function. This is a time-varying function which represents the need of disinfection of each localization of the map at each time. This function depends on the human frequency of access to each area, which is included in the probabilistic map through the probability to find a human. That's it, P sub H. Then also consider the environment recognition through the probability of a function of furniture and the elapsed time since the last disinfection. Capital T is the time that determine the need of a new disinfection. Then the path for the disinfection process is defined by connecting the point of the of the free ways, which is the mean value of the intensity function at each position. Therefore, the vehicle will navigate closer to the areas with higher disinfection requirements. The control algorithm for the path following navigation is also taken from previous work of our group. And it is an inverse kinematic controller based on the extended kinematic model of an autonomous vehicle. Well, I will not go into details, but the important thing is that in path following control, we can regulate the reference velocity to follow the desired path. And this allows us to regulate the intensity of disinfection of each area. With this aim, imagine that the red dot is the disinfection point with a disinfection intensity associated, and R max is the maximum distance with admissible irradiation. For our lamp, this distance is about 2.5 meters. So the disinfection point would be irradiated along distance E. E is the disinfection interest region, and as I tell you before, the red point is the disinfection interest point. This way, we can compute the desired road velocity at which over the interest region E, we can guarantee a proper disinfection considering E and the time needed to kill the virus. Then some auxiliary functionalities can be included, for example, obstacle avoidance, sound alarms, or automatic stops in critical situations. Well, the experimental setup includes a mobile robot, which has been fully designed and constructed in our institute with a fixed UV lamp. Well, we also use an Intel RealSense camera for both for static mapping and for the probabilistic mapping. The software used for the mapping is an RTAD map, and we also use the NUITRAC library for people recognizing. We also use an UVC light meter in order to calibrate our lamp. That is to get the curve of irradiance by distance. And considering the reported energy needed to kill SARS-CoV-2, we can get the time disinfection needed for each distance. For example, if the lamp is 1 meter from the point we want to disinfect, we need 40 seconds of irradiance. On the other hand, the Intel RealSense camera allows us to detect up to 6 persons simultaneously, obtaining their position with respect to the robot. And this information is included in the probabilistic map. As we can see in this video, the human detection algorithm extracts the human from the environment and computes its relative position with respect to the camera, which means also with respect to the robot. And this information can be included in the probabilistic map. As a preliminary result, let's see this sector of our institute. It includes a corner in the corridor. the initial path considers the safety way to travel the corridors. This path is designed for the slam. Whereas the robot update the map, also the human positions and movement are included, as we can see in this video. The position of the humans are included in the probabilistic map. Once the exploration finished, the map, as I tell you before, the map now includes the zone with disinfection priorities. While these couple of small yellow spots are noises due to the camera and the image processing, but the most important value are the zones where people were detected. Then the path, the new path for disinfection is planned by considering this zone, and the robot will approach them during the disinfection processes. So the robot will navigate along this new path with the velocity computed with the map information, the need of disinfection function, and the time needed to kill the virus in order to guarantee a proper disinfection of each area. And finally, as a conclusion, it has been developed a strategy for precise disinfection for COVID-19 in an indoor environment. The work is currently under development by the Instituto de Automática, but we consider that these preliminary results are good to continue working for tune these algorithms, and we expect to interact with health professionals to help us to in the implementation and to have the better functionality in the disinfection processes. Well, this is all I have to tell you. I hope you consider that the work is interesting.
Thank you very much, Professor Flavio. It is really interesting to see also a real robot employing this kind of technologies. So thank you again very much. And thank you to all of our presenters that shared with us your developments. So now I'm going to let Professor Carlos do the closing of the event.
Thank you very much, Sergio, for managing all the event. I think it had been on time, and we had the opportunity to see a lot of works doing around this topic. And so in the future, we also have a lot of collaborations to work. The idea of this project is a seed to get more funding, to also invite the participants, the audience, to be integrated in these projects. So we are very happy with that. Before, I don't know if we have questions, but before that, I would like to ask the presenters, the speakers, to take a picture. We can all run the cameras, please, for a moment. It's also great for the report of the project. You know how put that in gallery view? Maybe Sergio, you know more, and you can take another picture in large gallery. I don't have this option here, large gallery. Maybe you have.
I am only seeing six cameras active.
Okay, the people are still coming to the picture. Yeah.
Yeah.
Thank you very much. I don't know if we have any question from the audience. Maybe the people are a bit tired for the long journey today, and let's see, we have some questions. Okay, perfect. Even if you have to discuss later, we are open to that in the laboratory or by chat. Thank you very much for the speakers. We are closing also the project this month. Maybe we will do a meeting regarding more the objective that we had and that we got with the project, and in the future see possibilities of funding or more collaboration. Thank you very much for everything, and see you in this opportunity in this event, hopefully in person. Thank you very much.
Thank you. Goodbye.
Bye. Thank you.
Thank you, everyone.
Goodbye.
Bye-bye.
Thank you.
Thank you
Bye-bye.
Thank you very much. Goodbye.